Perfect. Well, thank you very much, and thank you, Stella, for inviting me. So that's a real pleasure to be here and present you what's going to be, or what was basically I'd say 5 years of work, maybe more now, 6 years of work when I was at ETH. So on the mechanical properties of nacre-inspired composites. So as I said, I'm now at Imperial since about 2 years now, so I'm starting a group there. But before that, and that's why I want to start with the acknowledgement, before that I was a postdoc and scientist in the group of Andre Studart. Let me get the pointer. So the group is quite big, and you can see that there was actually a lot of very, very talented students involved in the study. Actually, one of them now, Hortense, is a professor at Singapore. So you see, it's been a while we started that. And so you'll see their faces basically coming up during the lectures, and you see what they did and how they contributed to this research. And of course, we were funded by the Swiss National Science Foundation. So that being said, I just want already to start on maybe the first question of this presentation is why we actually look into natural materials and processes. So you see, I'll be talking with nacre-inspired composites, so something that is inspired by seashells. And so the first question is, why do we look into that? Well, if we actually plot the fracture toughness versus the Young modulus in an HB map, so it's just a map to summarize all the materials property for synthetic material this time, you see that basically we end up with ceramic here that are extremely rigid, so extremely stiff, but with extremely low toughness as well. Whereas for metals, we have something that are moderately stiff, but extremely tough. And we also manage now to make high performance composites, and they go up here in this diagram. And the thing you see is that if we actually try to put a trend on these data, you can see that we basically end up with, it's colloquially called the banana curve. But what would be very interested is to get to somewhere here, right? Where we can have the best of both, where we have a very high toughness and a very high stiffness, and hopefully very high strength. Well, when you do the same type of plot, almost the same type of plot for natural materials here, and you plot the toughness again versus Young modulus, what you end up with is, if you mix calcite here, so calcium carbonate, and you mix with some protein, what you end up with is the properties of this material here. That is the seashell that we're going to look into more details today. And you can see that, well, this time the trend seems to be completely the opposite. So we get something that is extremely rigid, extremely stiff, but we also get something that is with a very high toughness. The other very good structural example we know is, it's the same story. You mix calcium phosphate or hydroxyapatite, and you mix it with collagen, so again another type of protein, and what you end up with is bone or antlers. And you see again, we get to something that is very stiff but also has very high mechanical properties. So that's why we start looking into it, saying, we know this composition, we can actually synthetically reproduce more or less each of the components of these natural materials, but where we end up in trouble is that we don't, at the beginning we didn't understand why these mechanical properties were so high. The thing is, before going further, I just want to be fully honest there, and that's the personal distinction, but I separate bioinspiration from biomimetism, because we don't really want to reproduce exactly the composition and properties of these natural material, because if you plot them this time within the same graph, what you can see is that what the seashell that is apparently the best, or one of the best natural material we can have in terms of toughness, well, you can see that it's just as good as our synthetic ceramics, the one we can produce today, right? So I don't want to convince you, that seashell are great to build planes or any component. The thing that I actually, want to show is that if we understand how, you can change the structure of calcite by mixing it with a small amount of protein and get here, well, maybe we can do the same with our ceramics. So we can mix a bit of polymer metals or even other ceramics with our synthetic ceramics, and hopefully, we can bring the the materials property up here. So we need to just understand how this natural material works, but we don't really want to focus on making the exact same composition. So as I said, nacre is probably, I mean, it has been extremely studied over, I mean, I want to say 20, but it's probably more 30 years now, because of this very high toughness. And what you can see is, so if you look just in terms of composition, you have 95% of calcium carbonate, which is basically chalk, right? So it's a very weak mineral, with 5% of a protein that serves as glue inside. And for, you know, as I said, it might be a very French problem, but if you ever try to open oysters, right, you know that it's quite hard, it's quite tough, and it can become a real mess if you're doing it wrong. So these materials, just by mixing these two components that seems very, very weak intrinsically, well, you end up with something that's actually very strong and very tough, again, compared to the natural, you know, the building constituent. So in terms of microstructure, so this is a SEM of nacre, and you can see that it's constituted into, well, these are 10 micron, maybe 10 micron width platelets by 500 nanometer thick. And there is actually the mortar, so the protein is just around all of these small bricks that you can see here. And that's why you only have 5%, because you only need to basically get there at the interface, but the rest is these perfectly packed platelets. So besides the pictures, if you look at the properties of nacre, what you see is that when you start, so this is a curve in a stress strain curve in bending, and you can see that for actual nacre, the things that drove people to this natural system is that when you start testing it, well, you see something very interesting for something that is almost a ceramic, which, you know, this is a pure crystal of the same mineral. You can see it's very stiff, but it's extremely brittle. So when it reached the maximum strength, it just snapped. Whereas when you look at nacre, well, hydrated nacre, you can see that you have something that looks like a yield, and then you have some sort of plastic zone that goes, you know, for several fraction of a percent. But it's very, you know, it is irreversible, but if you actually unload, you still, you know, you still have a sample, right? So it behaves as if it was ductile, although it's not really ductility in the sense of metals. And what's even more interesting is if you look at different, you know, different species of nacre, you can see that you can get from very low toughness to very high toughness, and you can see very much this large, you know, this large deformation getting into the structure. So these white zones are the zone where the microstructure is working very hard to stop the propagation of a crack. And you can see that you can reach, you know, plastic zone or zone of damage that are extremely large for something that is, again, 95% a ceramic. So the reason why we have, we seem to have these very diffuse damages has been studied for a very long time, and it's still, nobody exactly know which part is very important, but we know that there are several levels of hierarchy in the microstructure. And the first thing we can look at is the first, you know, the long-range platelets alignment. So if you see over very large sizes, all these tiny platelets are perfectly packed together and perfectly aligned. If you actually zoom in more, you can see that while you have the platelets are very fitted together, you can even see, you know, some of them are actually interlocked with each other. And finally, if you look at the interface, then, you know, there's a real challenge to actually image that and doing correctly. But you can see that they're extremely complex because you have mineral bridges going on here, and you have the protein layer there. So you have a continuity in all the structure. You have a continuity of the mineral phase, even if you have some interface in between, some protein layer. And so if we try to summarize from these very, you know, simple assembly, what are the different reinforcing mechanisms that could happen during the failure of this material? Well, the first thing that we'll have to do to make this platelet moves to, you know, dissipate some energy during fracture is that you will have to break these tiny mineral bridges. And once these things are broken, well, because the platelets are not perfectly smooth and they're very tightly fit together, you're going to have also these asperities are going to induce some friction when you try to move it. And finally, I mean, you have these if you look just at the interface, you also have this organic layer that will just act as a glue, right? And so in shear, you're gonna have to shear the polymer, the protein layer as well when you're trying to deform it. Finally, something that is also present in the structure and has been looked at is that it seems like there's an interlocking mechanism during sliding. So you can see that some of these platelets are dovetail shaped. And so when you try to move these platelets, you will basically also introduce some compressive stress that will further stop the propagation of the crack. So that's all we know from this natural example. The only thing that we need to actually, well, the thing that we need to do now is actually, if I put a wish list of all the things we would like to have to be able to reproduce this structure, because again, we want to reproduce it with our material. Well, what we need to have is to have a process that allow us to control the structure at multiple length scale. We need to be able to control the local composition and orientation of different phases in the composites. And finally, we have an additional challenge, is that we need to achieve processing speeds that are compatible with industrial timescale, because 100 micron of nacre will grow in more or less 3 to 4 months. So we can't wait. Even if we would be able to reproduce the natural way of making this material, it would just be too slow. So we have to invent very much new processes to try to reproduce this structure and study their mechanical properties. And so that's what that's what we've been doing with the team at ETH, and now in London, is basically trying to pull up a toolbox of colloidal processing to be able to reproduce this structure. And today I'm only going to focus on this one, which is the magnetically assisted slip casting. So first, I'll go through a brief description of the process to get this composite, but then I will mainly talk about their mechanical properties. So in terms of process, we're using something that the team at ETH developed a while ago, and the idea is that it's using very low intensity magnetic field to control the orientation of anisotropic particles. So you start with, for instance, these tiny platelets, and we were lucky enough to find, so these are aluminum oxide platelets, so sapphire platelets, that are 10 micron in diameter and 500 nanometer in thickness, which is roughly the size of nacre. So that was already a good starting building block, let's say. And on the surface, we absorb super paramagnetic iron oxide nanoparticles, so these tiny blue spots. And what the team there realized is that because of the size of these particles, we're actually at a very sweet spot where you can actually align them with very little magnetic field. And we can control the orientation with very little magnetic field. So just to give you an idea, we're talking about millitesla intensity. So it's basically, you can control them with a fridge magnet. And I don't ask you to trust only my word, so I'm just going to show you a small video of how these platelet behave in the microscope. And you can see that we have this time a rotating magnetic field, so it's rotating out of the plane of the slide. And you can see that, so some of them already flip, but if you look at these particular platelets, as we increase the frequency of the rotating magnet, eventually it's going to flip. Right. So once you reach certain frequency, all these platelets are going to flip, and you can see that we're quite happy if we want to reproduce the structure of nacre, because we basically ended up here with platelets that are all aligned in the right direction in 2D, basically. So that's where we picked up the story, and we use this in addition to a very traditional ceramic processes. So that's how you make most cups and most dishes in ceramic. It's called slip casting. And so the principle of this process is very easy. use a, so you, in a mold, you pour your suspension. So the suspension is basically our particle inside water or any solvent actually. And you tune the composition of the slurry so that the particles are freely movable. So they can move around, they can be oriented, and you obtain a very liquid slurry. And what happens is you pour it on the substrate that is porous, so it's a gypsum substrate in general, or plaster. So a very cheap one, but a very easy to shape. And what happens is, because of capillary forces, the solvent that you have here is just gonna be absorbed inside your gypsum layer. And so you will build a layer here that's called a cake layer, where this time you actually concentrate so all your particles that were freely, that were freely moving inside your suspension would just be very consolidated and jammed together here. And so, of course, because this is time dependent, as you remove more and more water, the layer, this jamming front position, so the separation between these position where the particles are jammed and these particles are free, is actually moving over time. We can, we know the description, it goes at the square root of time, so we can very much predict where this cake thickness layer is going to be as a function of time. So that'll allow us to make some process control. And also, I just want to show you, so this time is the sample, that's the sample is the brown slurry here. This red thing is the magnet, and just show you how simple the actual setup is. And it's something, you can build with basically anything. And this time because the magnet is very heavy, instead of rotating the magnet, we rotate the sample, but the principle is the same. So if you look at the microstructure of a sample that has been made this way, you can actually see that, again, we obtain these nice platelets perfectly aligned with each other. They are nicely packed, and we can actually consolidate this assembly further using heat treatment. So we have the first step, right? Having this sort of structure. And now the question is, okay, now we have this first step. How can we, tune the mechanical, the different properties of the interface and of this platelet assembly to see if we can increase the mechanical properties and even better, understand where the toughness can come from. So that's the whole strategy of let's say, most of these presentations. So again, we're going to use the same alumina platelets, and what we're going to choose is change the interface structure in between and see what are the effects on the mechanical properties. And hopefully we will be able to see some of these mechanical, some of these reinforcement that we see in the natural example, but I'll detail that a bit later. So the first step is we started with polymer, because again, we think that this polymer, this in the natural sample, the polymer layer, the protein layer is going to act as a glue. And we also added some mineral bridges. So the microstructure, the cartoon is, have these very long platelets. We have silicon oxides, so mineral bridges in between. We can control the amount. And during the heat treatment, you would form some of these natural bridges. And in between, we infiltrate a polymer as a secondary phase. And with Tobias this time, what we did is actually choose 3 different polymers that has very, very different mechanical properties, and especially toughness. So you can see in the, in this stress strain curve, you can see the PLMA. Here is this green, so a very stretchy, very gooey polymer. You can see the toughness is quite low. And we then used PMMA, so plexiglass. That is also, so they're based on the same chemistry, and we just tuned the component to make them tougher and tougher. And so you see that we already increased by an order of magnitude the toughness when we go from PLMA to PMMA. And finally, when we go to PMMA and this copolymer here, we ended up with another orders of magnitude in terms of toughness. So we can span 3 orders of magnitude in terms of toughness for the polymer. How does that translate in terms of toughness for the actual composites? So we've tested in fracture, so in single edge notch beam test. We've tested these composites. And what we end up is, if we plot the flexural strength as a function of toughness, what we see is that more or less the tougher the polymer, the better. So, okay, it kind of makes sense at the beginning. And we can see the tougher polymer here has the higher toughness and more or less the highest flexural strength. And if we plot actually the resistance to crack propagation, so this time we do an R-curve. So if you plot the value of toughness as a function of the crack extension from this initial defect, you can see that, so that's where the crack initiate, that's the value at which the crack initiate. And the good thing is for all these material, well, actually, we see a rising toughness, so a rising R-curve. So the crack is harder and harder to propagate as the material present more and more reinforcing mechanism. So I just want to make a side note here on this polymer phase, because to present you something, an even more recent study here that we did with Tommaso. And we've actually changed the system, but the principle is the same. We have silicon oxide platelets, and we found a polymer that actually have the same refractive index match, the same refractive index as the platelets. So we ended up with something that is transparent. So first, just to say we can actually make these transparent, but something also that we've upgraded is our setup to look at fracture. And you can see here that's an SEM in situ test, where we open a crack, and you can see we use that to observe how actually the microstructure interact with this crack and what mechanism happens. So you can see we have a bit of deflection, right? But what is most interesting, I think, is that we can see this bridging polymer here and here that actually, you know, stopping the crack from opening. And so we think that one of the main mechanism of reinforcement in this type of composition is actually polymer bridging, as in, you know, technical composites. So if we look at the strength versus toughness of these material again, well, we ended up with something that is almost, I mean, quite as strong and even a bit stronger than normal glass, but also a lot tougher compared to transparent, other transparent materials. Right, so if we say we've looked at the interface in terms of polymer, so the tougher the better. Now if we look at the effect of mineral bridges, where it was actually quite hard to control already before, so we had to design a completely different composition to be able to control very finely the amount of mineral bridges. So this time we took some, again, commercially available alumina platelets. They have a titanium, so a titanium oxide coating directly made on the surface. That's how you can buy them. And we just put a polymer around it. The good thing is because of this, because these two solids don't really like each other, when you start heating up, the coating here actually start de-wetting. Well, or actually start, you have some coarsening of the grain here. And so you can see we can go from, you know, at 700 degrees, when you heat it up, you can see very small grain at the interface and some bridges here, to something that is very much coarsened and very bigger mineral bridges. So the first challenge was to be able to actually quantify the number of mineral bridges in a you know, meaningful way. So what we did is, what works with us there is that the contrast of this interface is very different than the rest of the composite. So by image analysis, we're actually able to separate the interface here, and we're actually able to measure the local thickness. And what we can see is that we have a nominal thickness of the coating here that is around 50 micron. But as soon as you start bridging these two layers, you start measuring effectively larger thicknesses. And so by plotting this distribution of thickness here, you can see that as we increase the temperature, we form more and more bridges. And so just by getting the fraction of bridges that are larger than a certain limit, we can say that, okay, this one is a bridge, or this one is just the normal coating we get before. And so going further, we are able to quantify this number of bridges. The only problem is that we also have many other different parameters that could play a role in the mechanical properties. And the first thing would be the density, for instance. So we would need to be able to have, with the same density, different mineral bridges fraction, so that we're able to very much isolate this effect. And so first we upscale the size of the sample we could make. But we also, what we did is change the processing parameter, so in terms of temperature and pressure. And we drew just a map of the different the density we obtain for these different composition. And now we can choose, we can select a path where we are sure we have exactly the same density of material, so the same amount of mineral in our composite at the end. But we actually, because we change the temperature, we change also the volume fraction of the fraction of these bridges independently of the density. Now, what was really interesting is we found that if you look at the flexural strength as a function of this mineral bridge fraction, what you can see is that for a long time, the trend is actually quite linear. And it seems to tell us that it just follows a normal shear-like model. So the stronger the interface, the stronger the composites in this case. And at some point when we have a too high bridging fraction, what we end up is starting to break some platelets. So we start seeing some platelets failure. So the interface is so strong that we start breaking these platelets at the end. And if we look now with the just the SCNB curve, we can see that we go back to having something almost brittle, in the sense that you have some stable crack propagation, but very little. But the toughness is actually increasing. And I mean, we get toughness value that are around 8 MPa square root meter, which is very, very high for mineral-based, let's say, material. So we get very high initiation toughness, but we get also, we got rid of the nice R-curve behavior, so the reinforcement behavior going on that we had before in this case. So there is something coming up with the metals, but the only thing I will basically say here to spend more time on the ceramic one is that metals behave, the simple rule that we design here are applicable to the composite with metals. It is actually, even if it's a lot tougher, it didn't change that much the mechanical properties in the end. And so that's why I think I will focus more on the ceramic one, which is a bit more surprising. So this is actually a bit of an old story now. So these materials they have been developed during my PhD with Sylvain Deville in Saint-Gobain. And so what we found out at that time is that so we made the sample with a completely different process. But what we found out is if you, at the interface this time, instead of trying to put another type of material, so polymer or metal, if you try to just put a mineral phase, so in this case, it's going to be a glassy phase, so silicon oxide based. And you also put these nanobridges, what you end up is something that has, when you try to test it in crack propagation, you have, again, initiation of the crack that is quite high, but you also have a very stable, slow crack propagation, which is quite unusual for something that looks like a bulk, a very bulk normal ceramic in aspect. So we revisited this material with this brand new process we had, because we could control we had a better alignment, we could control a bit better the structure of these and the density of these composites. So again, if we just look at the microstructure, you see we have alumina platelets this time, so the same one we used before. And this time the interface, we replace it with a silicon oxide glass. And we have these tiny nanoparticles as bridges again between these platelets. So we can make quite large sample, but before going to the value, I just want to show you how these ceramic break. So this is a sample, that's been tested in bending, and we really try to open this crack. And what you can see here is that the crack starts here and actually gets highly deflected by the microstructure, and it grows in a very stable way. And we get to the second branch here that grows almost at the same pace. So you get some branching, you get a lot of different mechanical toughening mechanism. And Pedro, the one who did this video, the students who did this video now name it the mustache crack. So I think we're gonna have to keep the name for a while. But basically you have this highly deflected crack growing in a very, very stable way, even if we have a material that looks like a monolithic ceramic. So if we look at the mechanical properties where we reach a bit higher mechanical strength, and if we look at the SCNB, if you just look at the value, I'm just going to use this time two different values. So the toughness at crack initiation and the apparent toughness when we start having this second very brutal failure. So this is all the stable part of the crack propagation. And we try then to see if this interface again has a different has an influence on the mechanical properties. So we know the amount of interface is important, but we wanted to check if, you know, just the composition, so the strength of the interface is also good. And so what we ended up is teaming up with the University of São Carlos in Brazil, because they have a huge experience in ceramic and refractories, and they say, okay, if you're doing alumina, just use this compound, this aluminum borate. It's the best phase, you know, the glassy crystalline phase we know for alumina composites and alumina refractories. So you should just try to do that. So one of their student, Pedro, came to the lab and he developed the same procedure, but again, we changed only the interface here, the composition. And this interface composition should be stronger for one reason, because it's also crystalline. So it should be glassy when you heat it up, but at some point you will react with the alumina and form a crystalline phase, which in theory should be stronger than the glassy phase we had before. So again, we try to increase the interfacial strength and see if the mechanical properties works or increases. You can see, so the principle, the process is the same. The microstructure is very similar again. And if we look at the mechanical properties now, from no interface to the glassy interface to the crystalline interface, what we see in terms of strengths first is that we actually, for no interface, we are very typical, we obtain very typical value for alumina, so conventional alumina. And then if we start adding some interface, so some glue, this mineral glue in between, we get to a strength that is now almost higher than the best alumina we know how to produce. And finally, with this crystalline phase, we see that we increase a bit, again, the strength there. And in terms of toughness here for this second graph, so if you plot the toughness for all these different interfaces, what we end up with is, well, first, we're always a bit tougher than alumina, and alumina doesn't have naturally reinforcing mechanism. So you will never measure, I mean, it's very hard to measure stable crack growth in these samples. And so you only have an initiation value. But for our guys, we can see that basically we managed to increase the crack initiation toughness, you know, by almost a factor 2 by adding this interface. And again, we have very stable crack propagation here. So Pedro was very interested in high temperature materials, so we also tested these composites at up to 1200 degree. And you can see here, so this is the value we have, and it's plotted in the map of all the different thermostructural composites we are using actually today. So you can see, for instance, the nickel-based superalloy that are used for plane engines, or now the new generation of materials for plane engines that are the carbon-carbon composites. And so you can see that in specific strength, we are actually, you know, we're better in terms of specific strength as this different temperature. And the only thing that actually is very has better properties now is these carbon-carbon composites, probably because of their density, and I mean they're a lot more refractory. So if we try to look at how we summarize basically all these things I've been talking about, so if we look at the toughness for just any, you know, I've looked into the literature for any materials that has that is inspired by nacre, more or less the same microstructure. And if you plot the toughness as a version of strength here, what you end up seeing is that, you know, the polymer, so let me change some color. So you can see here we have basically our polymer that have medium, you know, quite interesting toughness and medium strength. If you now start looking at what happened when you put metals, where we have all the metals here that are here, right? And what is very interesting at the end is that if we just look at these ceramic composites, we ended up with something that has both, seems to have very, very high toughness and very, very high strength compared to all the other bio-inspired composites we had before. So something that was a bit unusual in the sense that we were hoping with these very, you know, tough ductile phases of metal and polymer to have a very high toughness. Well, actually, it seems like because of the mechanism, the deflection mechanism we obtain in these ceramic composite, we obtain something that is very interesting mechanically as well. So now if we zoom out even more, and if we try to put this material in you know, the broader context of all structural materials, let's say, and again, if we plot the fracture toughness as a function of strength, well, you can see we're just shy of these ceramic matrix composites. So the one that have been developed for maybe 60, 70 years now. And we are, in terms of strength, we're in the same ballpark as zirconia-based ceramic or silicon nitride-based ceramic. So let's say there's a lot of work to be done still, and it's clearly not, you know, the story is clearly not over, but we're still, you know, we're in the right ballpark, at least in terms of properties. Of course, if we could go higher, then it will be better for everyone, I think. So I only have 5 more minutes, so I just want to present you briefly another aspect of this work that this new slip casting process has enabled us, and also to show you the video of the mantis shrimp, because I think we should, everyone should see that at least once. So as I said, do you remember nacre, the nacre sample here? If we look at the microstructure, it's calcium carbonate, platelets perfectly stuck together, just slightly glued, right? And if you look in nature, one of the good things of nature is that you know that, you know, no matter how strong and tough you're going to be, there's something that's going to try to feed on you. And so if we try and if we look for a natural predator of these seashells, there's actually one. And maybe you can hear the sound. So that's a mantis shrimp. If you can look here, it has a hammer that's basically used to smash the shell. Right? And you'll see how the shell ended up. So all these, you know, this beautiful nacre, wonderful things, how tough it is. Well, these shrimp here just is managed to just crush it. And I just kind of go back to the den and have a nice lunch. And these actual mantis shrimp here, they are very hard to get into an aquarium because the hammer they have that, you know, break the seashell is actually strong enough to break the glass of the aquarium. So you need, you know, you need to be aware if you buy one of these that you need some proper reinforced glass, right? What is very interesting for us is if you look at the microstructure. So the composition is very similar to nacre. The composition is calcium phosphate this time, but again the properties are similar. The only thing that differentiates from this structure to this structure is the organization, the internal organization. And this time the reinforcements are in rod shape, and they are, you know, packed as a plywood structure or bulligan structure. So they are packed helicoidally in the hammer. And this is what people start thinking of the reason why the impact properties are so good. So again, just by changing the microstructure, we appear to be able to have a material that is a lot more resistant to impact than one of the toughest material nature can come up with. So the question is, how do we reproduce again this type of samples? Well, if you remember, we know how to predict, if you take the slip casting, we know how to predict where the position of this cake layer is going to be over time. And the platelets here are still free to move. So we can basically change the orientation of our magnetic field over time. And hopefully we will see a change in orientation of our particle, and again, try to make the same microstructure in the end. And so that's what we observe. And this is just an optical microscope. So you can see the bands here that are just coming from the different orientation of our platelets in the sample. And if you look at the microstructure in the SEM, you can see, so we have something like we call the wave microstructure. So you have platelets that goes like this inside your sample, then like this. So, and each layer, you know, you can program basically each layer orientation the way you want. And eventually we manage also to change the setup and make a proper bulligan structure. So this time the platelets are turning along their axis. So you can see we have, here we have platelets facing us, and here we have platelets on their side. And we can make very large sample. We can make, we can program the microstructure very, very robustly. And so the next question was how we can make them dense. And I definitely don't have time to go through the process. So we just used an old, again, an old ceramic trick that is called templated grain growth. And this time we obtain very large grain we use sintering kinetics to obtain very large grain in the end. But because we can control the orientation of the particles at the beginning, what we obtain is, if you see, this is just an optical microscope of a almost dense alumina sample, sintered naturally, well, without pressure. And you can see that if you look at so these are shiny bands, are when you see the platelets facing you. And if you look at the microstructure, when you zoom in, you can see that we have grain again that have these Boolean structures. So grain like this, then grain like this. And we can change the pitch the way we want just by changing the way we cast our sample. So the rotation, the time for the rotation of our magnet. So that being said, I think we're through with the 45 minutes. So I just want to summarize a bit what I've been showing here. And starting with nacre, so you see this is again one of the toughest natural materials we know of. And the microstructure is very interesting and has very different reinforcing mechanism. And what we've seen when we try to mimic it is that basically when we have a weak interface, and by weak I mean a different classes of material of interface. So if you have polymer or metals, what we end up with most of the time is we're going to have bridging. So we don't see all these nice, platelet sliding we would see in natural nacre. We only see, well, we see some of deflection and some of bridging as reinforcing mechanism. Whereas when we put something that is just mineral, so ceramic composites, we end up with a very high deflection when we try to propagate a crack inside the sample. And that's what brings the toughness. So we change the reinforcing mechanism just by changing, well, the mineral content, let's say, of this ceramic. And finally, just to show you, so something we've been playing with also a bit more recently is if we try to look at, mimicking the microstructure of this hammer of the mantis shrimp. Actually, we managed to make dense ceramic that have periodically varying grain orientation inside the microstructure, and so hopefully these guys will be also a bit more impact resistant, which for ceramic is also quite an interesting field. Not only toughness is good. So with that, I'll just want to thank you all for coming here and listening. And just as a side note, I just got lucky, let's say, and I got a 5 years grant starting next year. So there will be opening positions. So if you are students and interested in working on that, I'll post the position opening in the website. And that's it for me.